Okay, today we're going to be taking T-notes on 5.3 electric cells. We will be discussing primary and secondary cells, terminal potential difference, electromotive force, and internal resistance. Let's begin. Cells are direct current devices that drive electric charge in one direction, from negative to positive terminals. Cells are sources of potential energy in the form of chemical energy. The original chemicals inside the cell react, causing current to flow, which in turn cause electrons to gain energy. Batteries, for example, are made of one or more cells. A cell is a working unit inside a battery, but a battery can contain any number of cells. Below here is a diagram of a circuit consisting of a battery and a light. When the circuit is closed or connected, as seen in this diagram, the electrons go through the wire, lighting the light bulb along the way. The electric charges go from the negative end to the positive side. This is one way of describing how electrical potential causes electrons to flow through the circuit. Let's look what happens inside the battery. So batteries have three parts. There is a negative electrode, which is shown in green, and this encapsulates the entire battery. The positive electrode, which is shown in red in this diagram, and a liquid or solid that separates the electrodes, and this is called the electrolyte. It's important to note that the electrodes in a battery are always made from two different materials, so never both from the same metal. This is the key to how and why a battery works. One of the materials has an affinity to give up electrons, and the other likes to receive them. If both electrodes were made from the same material, this transfer of electrons would not happen, and no current would flow. So the positive and negative electrodes are separated by a chemical electrolyte. It can be liquid, but in an ordinary battery, it is more likely to be a dry powder. When you connect the battery to a lamp and close the circuit, chemical reactions start happening. One of the reactions generates positive ions, which are shown here in yellow circles, and the electrons, which are smaller brown circles at the negative electrode. The positive ions flow through the electrolyte to the positive electrode from the green line to the red one. Meanwhile, the electrons, which are the smaller brown circles, flow around the outside circuit, which is the blue line, to the positive electrode and make the lamp light up along the way. The electrons and ions flow because of the chemical reactions that are happening inside the battery. The exact reactions depends on the materials from which the electrodes and the electrolytes are made, and we won't go in detail in this slide. Whatever chemical reactions take place, the general principle of electrons going around the circuit and ions flowing in the opposite directions through the electrolyte happens in all batteries. As the battery generates power, the chemicals, also known as the reactants, that are inside are gradually converted into different chemicals or products. Their ability to generate power decreases as the reactants are used up. The battery's voltage slowly falls, and the battery eventually stops producing energy. In other words, if the battery cannot produce positive ions because the chemicals inside it have become depleted, it cannot produce electrons for the outer circuit either. Due to the chemical nature of the electrolyte, the electrons cannot just take a shortcut. They cannot hop straight from the negative electrode through the electrolyte and go to the positive electrode. The electrolyte acts as a barrier. The easiest path then for the electrons to get to the positive terminal would be to actually flow through the outer circuits as seen here in this diagram. Although there are many different kinds of batteries, there are only really two types. They are disposable or rechargeable. They contain two different kinds of cells. Cells that are designed to be used once and thrown away are called primary cells. These cells use chemical reactions from electrodes and electrolytes to produce electricity. Because the electrochemical reaction in the cell is not easily reversible, the potential energy in these cells is limited. Examples of primary cells are AA cells, which are also known as dry cells because the electrolyte is a powder. Here is an example of a primary cell. It is called the Leclanche cell because this was invented by Georges Leclanche in 1866. So in this diagram, a carbon rod is placed within a porous pot, and this is the porous pot, and this porous pot contains a mixture of powdered carbon and manganese dioxide. The porous pot is placed within a glass vessel that is filled with saturated ammonium chloride solution, which is the electrolyte. A zinc rod is also placed within the glass jar. The carbon rod is the positive terminal, and the zinc rod is the negative terminal. The openings are sealed with pitch to keep the ammonium chloride solution from escaping. When you create a closed circuit with the positive and negative terminals, chemical reactions begin to happen. Ammonium chloride splits into ammonium and chloride ions. The chloride ions move towards the zinc rod, so it moves towards the zinc rod, and transfer their electrons to the zinc rod, forming zinc chloride. Here we have the chloride ions combining with the zinc to create zinc chloride. The zinc rod attains negative charge due to the excess of electrons. Thus, the zinc rod becomes the negatively charged terminal, known as the anode. So from this equation here, we have the ammonium ions. These ammonium ions move to the carbon rod, and the free ions of the carbon rod neutralize the ammonium ions, forming ammonia and gas, hydrogen gas. The carbon rod becomes positively charged because it has lost some of its electrons, thus resulting in the carbon rod becoming a positively charged terminal, which is also known as the cathode. Other chemical reactions produce waste products such as ammonia, manganese oxide, and manganese hydroxide. So as you can see, by connecting a wire to the electrodes, the electrons will move from the negative to the positive and will produce a flow of electrons within the wire. Here is a more detailed look at what the modern-day version of Leclanche's cell's interior looks like. AA batteries, 9-volt batteries, and watch batteries are all called dry cells because their electrolytes are contained in a low-moisture paste, while a wet cell has electrolytes contained in a liquid, hence the difference in their names. All dry cells have a cathode, which is the positive end, which is made of carbon, and the anode, which is the negative end, most typically made of zinc, and an electrolyte, which is inside the cell, and this is mainly made of ammonium chloride and manganese dioxide, depending on the type of the battery. Self-discharge in batteries is when the chemical reactions reduce the stored charge of the battery. This self-discharge decreases the shelf life of batteries and causes them to initially have less than a full charge when actually put to use. Unlike primary cells, secondary cells, which is the second category, can be recharged simply by passing a current through them in the reverse direction to regenerate the original chemical reactants. When you recharge a battery, you change the direction of the flow of electrons using another power source such as solar panels. The electrochemical processes happen in reverse, and the anode and cathode are restored to their original state and can again provide full power. One reason why primary cells are preferred is due to the high self-discharge with secondary batteries. Examples of secondary cells are any batteries that we recharge, such as lead-acid batteries that is used to start cars, rechargeable batteries, and lithium-ion batteries in our cell phones. When you charge your cell phone, you're really just running the battery in reverse, and you're reversing the chemical reactions inside. Here is a secondary cell. This is a lead-acid cell, also known as a lead-acid accumulator. Accumulators are most familiar to us as large, powerful car batteries. A lead-acid accumulator contains 3 or 6 separate cells inside a tough plastic casing. Each cell contains lead electrodes that are plates. The first plate is of metallic lead, and the other is a plate of lead oxide. Both plates are placed in sulfuric acid, which is the electrolyte. During operation, the sulfuric acid is gradually turned into water, and the lead electrolytes react with the acid to form the product lead-2 sulfate and 2 free electrons. As the sulfuric acid becomes more dilute, as its acid is removed from the solution, the battery becomes unable to supply more charge. But unlike a dry cell, it can be recharged simply by passing a current through it in the opposite direction. So here we have where the discharge of the energy is going in one direction from negative to positive. And then when we are pushing the charge in the opposite direction and reversing the chemical reactions, so we get our original reactants, we are pushing it from positive to negative. Recharging reverses these changes. Electrons are forced from the positive terminal to the negative terminal, At the negative plate, atomic lead forms. At the positive plate, lead oxide is created, which restores the cell to its original state. Capacity is the measurement of a cell's ability to release charge. It is essentially the measure of a battery's stored charge. In another way, it is the maximum amount of energy that can be extracted from a battery under certain specific conditions. It can be affected by age, temperature, charging or discharging practices, conditions, to name a few. It is measured in amps hours. And in this example here, there are two cells that have varied capacities. Cell 1 can provide one current for 10 amps for 3 hours, so that would give you a capacity of 30 amp hours. For cell 2, we have 10 amps for the current for 5 hours, which gives us a capacity of 50 amp hours. And this means that cell 1 has a higher discharge rate than cell 2 and will not last as long. Because there is a variance of the capacity, there can be a varied level of discharge from a cell. It is important to know that terminal potential difference loses its initial value quickly, has a stable constant value for most of its lifetime, until it is followed by a rapid decrease to 0 as the cell discharges completely. This graph shows 3 different loads of varied currents. When each device is connected and is being used, the voltage drops over time as the stored energy is being used until it drops precipitously as the cell is at its end of its energy store. Internal resistance is resistance that comes from the cell itself and is measured in ohms. A cell can be thought of as a source of EMF, which is known as epsilon here, with a resistor that is connected in series. To help us visualize this, a cell is represented as a perfect cell of EMF attached in series to an internal resistance, which is given the symbol of lowercase r. When current flows through the cell, a voltage develops across the internal resistance. This voltage is not available to the circuit, so we call this lost volts, which is known as V sub L. Because voltage is a measure of energy and energy is always conserved, the EMF of a cell is equal to the sum of its terminal potential difference, which is noted as V sub TPD, and the lost volts V sub L. This gives rise to the equation of epsilon equals V TPD plus VL. We know that V equals IR, which is the potential difference equaling the current times the resistance for both the terminal and the lost volts. So for potential difference, which is the EMF across the ends of the cell, we have that the V sub TPD is equal to the current times resistance, and that is I times capital R, plus the V sub L, which is equal to, again, current times resistance, but we give the current as being the same in a series, and the resistance is different for the cell, so we have a lowercase r. This equation can then be written as epsilon equals I times capital R plus lowercase r. Here is an example for you to try. A battery is connected in series with an ammeter and a variable resistor R. When R equals 6.0 ohms, the current in the ammeter is 1.0 amps. When R equals 3.0 ohms, the current is 1.5 amps. Calculate the EMF and internal resistance of the battery. Take a moment and then start the video back up when you're ready. Alright, so with this problem, they gave you 2 separate scenarios. You needed to take the equation for internal resistance, which is this right here. Because we are given values of resistance and current, we will need to change the voltage into IR. So we get the equation solving for resistance as being IR equaling epsilon minus I lowercase r. When we plug in the variables for the first scenario over here and the second scenario over on the right-hand side, we get internal resistance of the battery as being 6.0 plus lowercase r for the first scenario and 4.5 plus 1.5 lowercase r for the second scenario. To determine the total resistance, we set these two equal to each other and we solve for r. So here we have them set equal to each other, we solve for r, and we get an internal resistance as being 9 ohms. The total power supplied by a non-ideal cell is P equals I squared times capital R plus I squared times lowercase r. This first I squared times capital R was covered in 5.2 part 2, where we calculated the power of a resistor. This second I squared times little r is for the internal resistance, or wasted power from within the cell itself. The sum of these potential differences is the total amount of the power supplied. We know that internal resistance equals I times capital R plus little r from an earlier slide. If we solve for current, we get I equals epsilon over capital R plus little r. When we plug that into the potential difference for the external circuit, for the external cell, we see that the power delivered to the external resistance is epsilon squared divided by R plus little r squared times R. The graph below shows how the resistance changes as the power is delivered to the external circuit. You can see that the resistance increases until the resistance of the cell and the external cell are equal. So when these two factors are equal, we get the maximum here, and then it begins to decrease again. All right, so we've made it to the end of our TNOTES. Here are 2 practice problems for you to try. Make sure that you have everything understood and completed and ready to apply this information in class next. Thanks for watching.